Welcome back. So we're just going to look at a few examples with numbers because there were no numbers in those other ones. So we can find the area under a curve by adding rectangles, and the answer is called either a Riemann sum or a rectangular approximation method. Okay? Either of them is used interchangeably. So just know it just means the same thing. We're approximating the area using rectangles. We'll talk a little bit more about Riemann in class. I'll wait till we're in class. All right, so the width of a rectangle is called a subinterval. All right, so how many subintervals are we going to have? Right, that's our width, and our subinterval is always change in x. It's because a subinterval is just the width, and the width is the same as the change in x. Let's put that there. Width. Come on. Change in x, which is just the ending point minus the starting point divided by how many subintervals do you want. Okay? So the definite integral is then given by the area under the curve. Hey, weren't we integrating when we were finding antiderivatives? And this is the definite integral. How do those two things relate together? How does finding the function by doing the derivative backwards equal anything with area under the curve? You'll find out. Just not in this podcast. And maybe not even in this lesson, but you will find out. All right, so n is the number of rectangles. Okay? So if we take and this will become important a little later on in this lesson. Okay, so just kind of take it in. All right, we're going to come back and see this a little later on. All right. So the limit as n approaches infinity, in other words, as n is the number of rectangles, as our number of rectangles keeps on increasing and goes to infinity, we get more and more and more and more and more and more rectangles. Okay. The sum of the heights times the width of the rectangles is going to give us the area under the curve. And as n goes to infinity, it's not going to be an approximation anymore. It's going to be the exact area. That's for a later lesson altogether. But I did want to introduce that idea to you. Right now we're approximating the area. Eventually we will find the exact area. So where it says f of c, so f of c is the value of the function. F of c to the k is the sum of all the values of the function, right? Because we don't want to, we could do this an infinite number of times, but I think we would be tired, and it would be tedious, right? And there are ways that we can get all those sums at once and just multiply it one time by the width of the rectangles. But right now we're going to be approximating, not finding the exact area. But I did want you to know where this is leading to eventually. So, more on just an introduction to Riemann sums. So if f is continuous on AB, and if the value of our function is greater than 0 for all x in AB, so that means that you have no negative numbers, just you're above the x-axis for that interval. For all x in AB, then the area between the curve y equals f of x and the x-axis over an interval AB is defined by the limit, and so it's the exact same thing we saw before. So it's the limit as the number of rectangles goes to infinity, right? And then this one has a k instead of this one had a c instead of this one has an x instead of a c, same thing. All right, so f of x to the k, f of x star to the k there, just means the sum of all the heights. And you should know that sigma, by the way, and I have it on a later slide, I know. Sigma equals sum. That's what it means. So the sum of all the heights, and this is the width. I should say of the rectangles. Width of rectangles. Gee, if you what? So a little thought to ponder here. I'm not going to answer the question, but I just want you to ponder it. If the number of rectangles is approaching infinity, what's the width of the rectangles approaching? Just something to think about. I will answer that question, but not today, and not right away in class. But eventually, I will answer that question. But you think about it and see what you come up with. And then when I'm ready to answer the question, I'll see what you thought. Moving on, let's now look at just approximating the area. So we're not going to be dealing with limits in this part of the lesson. We are going to be dealing with just what we started off with. Oh, there it is, sigma sum. Told you I had it on here. And that is finding the area under the curve. And I do have these ones written, and I will give these to you written. And I will have us do some together so that you can write it out, so it can make sense to you because you wrote it out. But realistically, I don't want you to have to spend 20 minutes writing down this problem if I can give you some of the information. All right, so divide the interval 0, 2 into n subintervals. In this case, our n equals 5. So that the width of all the rectangles, change in x's width, they're all 2 fifths. Right? So every one of those has a width of 2 fifths. These end up being inscribed rectangles. Right? So these are inscribed rectangles, same function as going to be the next problem. So the height's going to be calculated on the right. The question really generally isn't going to be asked as do the inscribed rectangle. You'll either be asked right, left, or midpoint. Right? So in this case, if it's inscribed, what we're really being asked to do is use right-hand rectangles. You may have to figure it out, but most times you'll be asked. Right? And if we draw our curve and it says inscribed, it means the rectangles can't go outside the curve. If I do a left-hand one, notice that they would go outside the curve, like for instance up here. So if I do a left hand, see, I'm outside the curve. So that's no longer inscribed. Most of the time, though, you're just going to be asked on the right, left, or midpoint. So this one is a right hand. Right, so that means where the right-hand side of the rectangle, as soon as it hits, we stop. Right? I had to approximate a little bit, kind of draw lines and try and figure out where they went on this graph. So it looks like the first rectangle is at 4.8. I think seems pretty, so we agree with that. Looks like the next one is at 4.4. The third rectangle hits the curve at 3.8. The fourth rectangle hits the curve at 2.4. And the last rectangle hits the curve at 1. Right? And here we were given a graph, right? Matter of fact, we don't even know what the function is. So you couldn't plug into the function, right? You would have to draw the rectangles under the function that you're given here. All right, so the width is going to be 2 fifths. We're not going to multiply each and every one. Please do not distribute 2 fifths to each one. That is just way more than you needed to do, and the hard way to do it. Instead, add up all the heights and multiply by 2 fifths one time, simplifying the parentheses. All right, so nicely that they all have the exact same, I just changed, by the way, all of those decimals into fractions. Right? And it's nice they all have the exact same denominator, makes adding really easy. Right? And since, rather than changing 2 fifths to 0.4, it'd just be easier for me to change those decimals to fractions. The multiplication is so much easier. All right, so 4.8. All right, so 4. If I want, so what's 4? How many fifths would we have if we divide 4 into fifths? You'd have 20, right? Because 5 times 4 is 20, and then that's 8 tenths. Right? So 8 tenths is the same as 4 fifths. So 24 fifths. All right. Hopefully, changing to fractions is no big deal for you all. So 24 fifths plus 22 fifths plus 19 fifths plus 12 fifths plus 5 fifths. Right? We add those all together. They add up to 82 fifths. Multiply it by 2 fifths, and we get 164 25ths. So the area under the curve is approximately 164/25. Why do I say approximately? Look at all that white space. That's under the curve. That's not part of a rectangle, right? So of course that's an approximation, and it's an underestimate, right? There's no. I don't have any area in my rectangles that's outside the curve. I have area, all my rectangles represent area inside the curve, but then I've missed some things. I missed like some curvy triangles there. Right? So, but this is what our approximation would be if we used a right-hand Riemann sum. And we're moving, and we're moving. And we can still look at this lovely picture. There we go. Same function. Now it's a left-hand Riemann sum. All right. So now I have it's the circumscribed, and that means that I'm going to make sure that I have nothing. I don't have that. I hit the right-hand side. My rectangles are going to go. I'm going to choose the maximum value in this case. My rectangles are going to go outside the curve. All right. So this is a left-hand Riemann sum. All right, so on the left-hand side, all right, we're starting at 0, and 0 looks to be 5. Right? Same, by the way, same change in x. It's still 2 minus 0, end value minus starting value divided by number of rectangles. That didn't change. All right, so we have 5 is the first value of the function, and then the next value, 4.8, appears to be where this rectangle hits the curve, so it's on the left-hand side. It looks like it's about, except for that line there, looks like it's about 4.8. Looks like the third rectangle hits at about 4.4, the fourth at 3.8, and the last one at 2.6. All right, so now we add up, we change those to fifths, so it makes it nice and easy to add them up. So we have 25 fifths plus 24 fifths plus 22 fifths plus 19 fifths plus 13 fifths. So just all those numbers change to a fraction. All right, and then we add them up, we get 103 fifths. We multiply by the change in x, 206/25. This time it's an overestimate, right? So what's our area? Well, somewhere between, the actual area is going to be somewhere between the first value, which I forgot what it was already. I hate it when I have to change pages. Should have made sure I wrote down 164/25. So obviously it's more than 120. It's more than 164/25 because we got all that white space we didn't represent. So that one was an underestimate. Here, there's nothing under the curve that's not represented. Matter of fact, we got a whole bunch of stuff that's not under the curve, like this and this and this and this and this. All right. So this time it's an overestimate. Right, so it's less than 206/25. So it's the actual is somewhere in between the two. But we're not looking for the actual. We're looking for an approximation using rectangles. Right? So our right-hand approximation was 164/25. Our left-hand approximation is 206/25. But you should know whether your approximation is going to be an underestimate or an overestimate. And we're waiting for the page to turn. All right, so here we have one more. Actually, I'm going to do two more, but I'm going to do, my last one's going to be a couple different ways. All right, so given the equation y equals x squared plus 1, find the area under the curve from x equals 1 to x equals 4 using 5 left-hand rectangles. So it's the left-hand side that's going to hit the curve. All right? All right, so we will use, notice that we will use x equals 1, right, where 1 hits the curve, and where, so since the width here is, let's put that over here, so the width of our rectangles is 4 minus 1 divided by 5, so that's 3/5, right, so each one of these, that's 3/5, so it just means the width here. So every single one of these rectangles has a width of 3/5. So if I add 1 and 3/5, that's going to be 8/5. So this right here is 8/5. Right? and I should say x is 8/5, we have to find the value of the function, and it has it listed above too. All right, so we find the value of a function at f of 8/5. That's just 5/5 plus 3/5. And if we add another 3/5, 8/5 plus 3/5 is 11/5. And if we add another 3/5, 11/5 plus 14/5, 11/5 plus 3/5 is 14/5. And if we add another 3/5, we'd get 17/5. So notice that we're just adding 3/5 more each time. So we have to, so we're going to be drawing graphs for these, not to have these perfectly represented graphs, but just to be able to figure out what value of the function that we're using. And sometimes it helps to see it, especially in the beginning. All right, so the width of our rectangles is 3/5. The height of the rectangles is going to be our first value, f of 1, plus f of 1 plus 3/5, plus f of, now it would be 1 plus 2 3/5, right? Because now we added 2 widths. So here I'm just wanting to make sure that you understand where we get the x values that we plug in. Right? So we keep on going. Right? So we've got 1, we've got 2 3/5, now we need 3 3/5. So we have f of 1 plus 3 3/5 plus f of 1 plus, and we have one more there, 4 3/5. Right, so those are all the heights of our rectangles. So in other words, we add up f of 1 plus f of be 8/5 plus f of 11/5. Sorry, that's a 5, not a 6. Looks a little like a 6. Plus f of 13/5, and then plus f of, 14/5. 11 plus 3 is 14. Plus f of 17/5. Right? So that's the height of our rectangles. Right? It's all the values of the function at those locations, and the width is 3/5. Our Riemann sum, right, is just going to be our area approximation is going to be 3/5. Okay? And then times the value of the function for each of those. So let's write down what they are, because we'll actually get a value here. All right, so f, and we know what our function is, right? So f of 1, I'll put it somewhere over here. All right, so f of 1, would be 1 squared plus 1, which is 2. F of 8/5 is going to be 8/5 squared plus 25 25ths, because if I square 5, I'm going to have, I need a little bit more space. I'm going to have 25 in the denominator there. So that's going to be 64 25ths plus 25 25ths. So that's going to be 89 25ths. Hopefully everyone's okay if I do that, because I'm taking a lot of space up here. All right, so 8 squared is 64. 64 plus 25, 89, right? And then f of 11/5 is going to be 11/5 squared plus 25 25ths. So that's going to be 120, I'll just write it like this, 121 25ths plus 25 25ths. That's going to be 146 25ths. Ooh. And then we have f of, why do I keep wanting it to be 13/5? I know it's not 13/5. F of 14/5. So we'd have 14/5 all squared, and plus 25 25ths. So that would be, when we square that, that's going to be, I'm not going to bother write that. I'll just write the answer. So 196 25ths plus 25 25ths is going to be 221 25ths. And the last one there, f of 17/5. So we have 17/5 squared plus 25/25. So that's going to be 289/25 plus 25/25. So that's going to be 314, right? Yes, 314/25. Okay, so those are all our values of our function. Just kind of squeeze them over there. Now, normally you won't write all this f of 1 plus 3/5, f of 1 plus 2 times 3/5, right? But you would write f of 1 plus f of 8/5 plus f of 11/5, right? I just put that first part in here, this part here, just to kind of help you see where the values came from. And now I need the values. All right, so our area is going to be 3/5 times, I'm going to change 2 to 25ths so I can add them all together, 50/25 plus 89/25 plus 146/25 plus 221/25 plus, squeeze it in there, 314/25. Right, and so that's going to be 3/5 times. So now I gotta. Sorry, I just did all that math in my head, and I want to finish this podcast. So I'm just adding them up. That number there that looks so weird is 314. So 820/25. And that would reduce, because 820 is divisible by 5. It's 164. All right, so our area is going to be 164 times 3, 492/25. And hopefully I didn't hit anything wrong on the calculator. So I'm trying to hold the microphone at the same time. All right, so that is our area using our left Riemann sums. Now, is that an underestimate or an overestimate? Well, I see some triangles, roundy triangles in the curve that are not represented. So, of course, this is an underestimate. Also, a little note there. You do not calculate f of 4 left-hand rectangles. So it's always the left-hand side. So you never get to the last value. If it was a right-hand rectangle, you wouldn't use the first value, but you would use the last value. All right, so we're going to take a look at one problem, super easy one, and it's all already written down for you. It's written down for me, I should say, because I did all the writing. You just watched me. All right, so we're going to calculate Riemann sums for the function f of x equals x cubed on the interval from 1 to 5 using 4 subintervals and choosing either a left endpoint, a right endpoint, or a midpoint. In other words, we're doing the same problem 3 times. So we're choosing the left endpoint, the right endpoint, the midpoint. Here's what the problem looks like if we choose a left endpoint. So our change in x, our interval was from 1 to 5. So that means we would use 1, and let's talk about our change in our x first. So our change in x can't be any easier. 5 minus 1 divided by 4 is going to be 1. All right, so the width of all of our rectangles is 1. And normally we won't do it like this. It's just typed in that way. Normally, but we would do 1 times, but you really don't have to do 1 times. All right, so that's why it's written like that. There's nothing to multiply at the end if our change in x is 1, right? So the height is the area under the curve, is the area of our rectangle since the widths are all 1. All right, so we would use f of 1, the first value. right? And then we would add 1. We would use the next rectangle would hit at 2. And we add one more change in x, so then the third rectangle would hit at 3, and the fourth rectangle would hit at 4. Notice we do not use 5, right, because it's always the left-hand sides. So we're using our starting value, not our ending value. And when we add that up, the area is 100. This one is an underestimate because we can see all that space that's not represented in the rectangles. Here we have the same thing, but a right endpoint, which is coming very soon. Right here. All right, so now notice we don't use f of 1 because it's when the right-hand side hits the curve. So our first rectangle is going to be it's going to be our starting value 1 plus a change in x, and a change in x is 1. So we're going to start off with 2. And then we'll use 3 as the second rectangle, 4 for the third rectangle, and 5 for the last rectangle. Okay? So now we're using where the right-hand side hits the curve. And now our area is 224, and that's an overestimate. You can see that we've got lots of rectangle that goes outside the curve, and we've got everything under the curve plus more. All right, now remember, the first one was 100, and the second was 224. And let's look at the midpoint. So 100 plus 224 is 324. That's something I want to point out. So 100 plus 224 is 324. If I take the average of those two, that would be 162, right? 162. Remember that because I want to point something out to you. As soon as the page turns, I want to point that out to you. Well, we'll continue looking at the right endpoint. It's beautiful. Notice what my area is. All right, so now this is where the middle of the rectangle hits the curve. So I don't use 1 and I don't use 2. I use the halfway point. So notice all of those values and I shouldn't say value, well, it's the value of x I want to talk about. So the value of x that's used to find the value of the function is going to be your starting value, your a, plus the change in x divided by 2. Right? So it's the halfway point. Right? So a here was 1. My change in x is, actually that's not a good way to put it, but it's the halfway point. I realize that I have to add, it's not the way I want to say it. So the value of our function that's used is the halfway point between, that's how I want to say it, the right-hand limit and the left-hand limit. And actually, let me say the left-hand limit because that's the smaller value. The left-hand limit, that's how I wanted to say it. Left-hand limit and right-hand limit. Excuse me. Oh, man. Thinking of limits now. Left-hand, the left hand and the right hand value. And of x, not the value of the function. Right? So for the left hand side, we would use f of 1. The right hand used f of 2. Halfway between 1 and 2 is 3 halves. So the mid point used halfway, 3 halves. Okay? That's what I wanted to say. I had to figure out the most eloquent way to say it. So it's the value of x that we're using is halfway between what we would have used for the left-hand side and the right-hand side. It's the value right in the middle of the bar. Okay? All right, so when we would plug in 3 halves and 5 halves and 7 halves and 9 halves, we'd get to those values that you see right there. And when we add them up, we get 153. Notice that, and this is very, 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 very important. I'll put the left first. So important. The left hand plus the right hand, oops, no T in my word right hand, divided by 2 does not equal the midpoint. All right, it is not the average, right? So the midpoint approximation is not the average of right and left hands approximations, values, areas, whatever you want to use. All right, it's the value that I plug into the function that's averaged, not the whole values, not the whole areas themselves. All right, it's not going to be smack dab in the middle. Yes, it's going to be between the two, because notice now I've got some that's hanging out and some that's left under the curve. And maybe the stuff that's hanging out kind of looks about the same as the stuff that's hanging over. Matter of fact, it's hard to figure out if you look at the midpoint whether this is an overestimate or an underestimate. I really can't tell, just looking at the graph, whether the stuff hanging over the function is exactly the same as the stuff hanging under. It kind of looks the same, doesn't it? So it's very hard to tell whether this is an overestimate or an underestimate. And so much so that we can kind of see, oh, maybe this is a little closer to the area of under our curve, a little bit better approximation. But notice that it is not 162. All right, it is not 100 plus, what was it, 2, whatever it was, divided by 2. All right, not at all. Okay, so do not average right and left hand and say that's midpoint approximation, or I will cry. All right, you're going to take the middle of the rectangle. All right, it's the value halfway in between, which it would have used for the left hand side or the right hand side approximations. That's the value you're going to use. All right, but the area you get in the end will not necessarily be the average. Matter of fact, 99.999% of the time, it would not be the average. Okay, so not good odds at all to try to average those and think that's the midpoint at all. All right, so this is the end of my podcast. All right, and this is all mostly just some introduction. We're going to be looking more functions and more right hand, left hand, and midpoint approximations. Bye for now.